Okay, cool. Hopefully I'm not going to be one of those people who takes too long to figure this out.
You have access? You good?
Yeah.
Yeah, your co-host. You should be good. Okay.
Okay, there we go.
Close the. Oh, there we go. Okay. All right. So thanks everyone for being here for the department seminar here or virtually, or apparently right upstairs, as the case may be. Couple quick announcements. I do want to thank all of the graduate students who've gone ahead and you saw my email last week saying that we want to get all the graduate students to set up Google Scholar profiles. And there's a couple reasons for this. First one, it helps you kind of curate your publications and your conference presentations. Trust me, in a few years, you're not going to be able to keep track of them. So it's nice to have a kind of a database that automatically updates these things. The second reason is because as an accredited institution, we need to actually track graduate student involvement in conferences and in publishing papers. Now, in the past, we used to do this whenever you would have travel authorizations, but since with the increase of virtual conferences, that's not a reliable resource to figure out what conferences you're attending. This will help us. This will help close that gap. And then finally, because we don't want it to be all about making our life easier, I did point out that starting in January, we're actually going to be using that database. We're setting up an alert system so that when papers are published and posted to the Google Scholar profiles, that we're trying to plan some form of recognition for the students whenever you have referee journal articles published. So, but that'll be the database we'll be using to draw from. So that is just to try to use more carrot, less stick to try to get you to get those Google Scholar profiles done. But I think we got 2/3 of the students have already set them up, so that's awesome. And thanks for those of you who've done it, and looking forward to seeing the profiles of the ones who haven't done it yet. If you have any questions on how to set it up, please email me or Mario, and we'll help you get it done. So I'm happy to introduce our speaker for today's seminar. As always, the question and answer will be posted either in the chat, which I will annotate those questions, or raise your hand virtually, or raise your hand in reality, and I will moderate the Q&A at the end of the talk. Our speaker today is Dr. William Walters, who is an assistant professor at Penn State University in the Ken and Mary Alice Lindquist Department of Nuclear Engineering. His expertise and experience is in the areas of reactor physics and computational radiation transport methods and modeling. He received his PhD in nuclear engineering from Virginia Tech on the topic of adaptive angular quadrature techniques for discrete ordinate transport methods. He has a wide variety of experience in Monte Carlo, deterministic and hybrid modeling of nuclear systems, including reactor physics, shielding, safeguards, and detector modeling. Current projects include development of low-order hybrid transport methods based on the fission matrix for multiphysics reactor modeling, safeguards of molten salt reactors, improving modeling and calibration of the Penn State. I'm going to apologize on this one. Is it Brazil? How do you pronounce the reactor?
Close enough. Brazil.
Brazil. That is closer than I usually get. Thank you. The Penn State Brazil nuclear reactor and modeling of nuclear thermal propulsion systems. And so with that, I hand the floor over to our speaker, and thank you again, William, for being here today.
Okay, thank you so much for having me, and thank you for inviting me out here. I hope this talk is at least somewhat interesting and thought-provoking. I would also add for the Google Scholar stuff, really helps your visibility in terms of jobs and other stuff like that, so people, first thing that's going to come up. So anyway, I'll get started here. Okay, there we go. So kind of overview of what I'll talk about. I'll just talk a little bit about, my overall research, what I do. And I kind of split up into two topics, one on molten salt reactor nuclear material accounting, and then one on fission matrix methods. So two pretty different things, but I think that's going to be more interesting than going too much into the detail on one of these things. So, my overall research, so first of all, making computational methods for reactor physics and radiation transport kind of problems more broadly. So, more from a kind of mathematical and computer programming point of view. But, I don't like to get too far away from, the physics and real world problems and stuff like that. So I try to also keep grounded in applying these things for useful projects. A little bit about me. So I grew up in Canada, went to University of Florida and then Virginia Tech, and then ended up in Penn State. So maybe that looks like a neutron trajectory to you. I think it looks like one. I got a couple beautiful cats. People like cat pictures, I guess. So I like to put that in there. So first I'll talk about molten salt reactors, right? So molten salt fueled reactors are, very popular concept, a lot of interest, a lot of companies kind of proposing to build these, and research being funded by the government. So, they have low pressure operations. There's a lot of different fuel cycle options you can do. They have some excellent safety characteristics, right? And what I'm going to look at here is mostly fuel on the low enriched uranium fueled reactors, which are, the most likely option in the near term, right? In the far term, there might be other things like thorium, fast reactors, stuff like that. So I'm just looking at the LEU fueled ones, though. So, when you think about nuclear material accounting, right, you want to be able to keep track of the nuclear material in your facility to make sure that no one's going to take it and do something bad with it, right? So in a regular solid fueled reactor, you have a bunch of items that you can count, right? Fuel assemblies, fuel rods, right? The number of fuel assemblies in, number of fuel assemblies out. You just go count these things. As long as you can verify it, there's no like fake fuel elements there, then you're good, right? Probably simplifying things a little bit, right? But it's certainly a lot easier. So what if you have a liquid fueled reactor, right? It's hard to kind of measure what's, measuring what's coming out. Like it'd be super easy for someone to just dump some extra salt in there that doesn't have any uranium or plutonium or whatever. And, you wouldn't be able to tell really, right? So what are you going to do? I guess, probably you need to measure the composition of the salt, and then see what you expect it to be under regular circumstances, and then see what you, and then what it would be under, kind of someone doing something illicit, right? So you're comparing measured versus expected, okay? But this really means that you need really accurate, both expectations and measurements, right? So if you measure, a 5% difference in some concentration, right, and you have some large measurement uncertainty and there's some other uncertainty in the problem, are you going to be able to reliably say that things are good at this reactor, right? Or are you going to be able to say that maybe someone has taken some of this nuclear material somehow? The other challenge is that for most of these, or for many of these reactors, some form of chemical processing of the fuel is planned, right? So that could be something as simple as removing noble metals from fission products from it, or the off gas system. When the fission product gas comes off, it's going to get taken off somewhere. But there'll also be online refueling usually, right? So we'll be adding fuel to this thing slowly over time, and then removing some of the used fuel. Okay, so there's like a bunch of loops in there, and places that someone could kind of potentially be doing some processes, removing some stuff, removing fissile material like plutonium from there. So, especially if someone was just like slowly bleeding plutonium off of the system, it would be pretty hard to be able to tell, right? So, even if someone is just diverting some small amount, over time, that's going to very quickly end up to be more than, a significant quantity of fissile material, right? So a significant quantity is, defined by the IAEA as some amount that could probably be used to make some kind of weapon. So I think for plutonium, that'd be like 8 kilograms. Okay. So to do this, right, we wanted to model some kind of representative system. So we used the molten salt demonstration reactor, which was, there's in the 70s, they came up with this design. The reason we're using it is because, there's a lot of publicly available information, including all the auxiliary systems and stuff like that. And other researchers are also using this to model the systems and safeguards analysis for MSRs. So this is like a lithium fluoride, uranium fluoride fuel salt with modified from the original design to use low enriched uranium. It's in these thin fuel channels with graphite moderator blocks in between. Okay, so we kind of want to look at first was what is the effect of protracted removal of plutonium on this system. Okay, so the overall model is kind of different from a regular reactor in that you have this primary fuel loop where you have this fuel going around, right, being circulated through, and that's being burned up. But at the same time, you're putting in fresh salt, fresh fuel over this cycle slowly. You're removing all the fission product, the gases from the system. Okay, so all this, xenon, argon, krypton, that's all getting bubbling out of the system and getting taken off somewhere. Most of the noble metals are going to plate out somewhere. They're not soluble in the salt, so they're gonna get removed from the system, either deliberately or just plating out on some pipes or heat exchangers, something like that. So, those are set up to be removed in this model. And then, since you're adding in stuff to this, right, you're adding in a bunch of salt over time, that needs to kind of overflow and go somewhere else. There's some other, spent fuel kind of tank over here. And then we also put in the option to, remove some amount of plutonium continuously over time, right? So, it could either be nothing there for the baseline case, or maybe up to 10 significant quantities, or 80 kilograms of plutonium. So we used two different neutronics models for this. One of them was Serpent, which is a Monte Carlo code, which is used a lot for burnup, and the other one is Scale, which is a code package from Oak Ridge that has a lot of neutronics capabilities. So, part of the reason for using two different methods here, right? It kind of complicates things, but a lot of the molten salt reactor capabilities, including this continuous feed and removal stuff, they're all really, they're pretty new, right? So we wanted to, make sure that they were working okay, right? So wanted to make sure, right? So if one of them's screwing up, right, we have the other one to kind of check and make sure it's okay. And also, they each have kind of unique capabilities. So Scale has a lot of good uncertainty quantification tools. And that's one of the key things here, right? Is that we want to know what the uncertainty in our compositions are, because we need these accurate measurements, or these accurate expected values, if we want to be able to compare them to accurate measurements to see if something is wrong. So in Scale, this is using Sampler, which basically just perturbs the cross sections and stuff in the simulation to calculate uncertainties. And we use Serpent mainly because it's continuous energy Monte Carlo, so it's super accurate, and it's also much faster than the equivalent kind of thing in Scale, just Kino. So you do things a lot faster, and it's generally just a lot easier to use than Scale, and the output's a lot easier and everything. So that's kind of the motivation there. If you look at K effective over this 8-year cycle that we have, they're definitely a little bit different. I think I've labeled that wrong. Anyway, the K effectives are not exactly the same in these two models. It's probably because of the thermal scattering, some of the limitations in the Scale for high temperature gas reactors. But also it's just the difference between a Monte Carlo model and a deterministic model with the discretization error and the multi-group approximation. So actually this this difference is expected to be reduced a lot in the next version of scale. So if you remove, 80 kilograms of plutonium, this is a, so you mentioned there's a 750 megawatt reactor concept, and it ends up producing a lot of plutonium over the lifetime, right? So removing 10 significant quantities, it sounds like a lot, right? But it only ends up changing the amount of plutonium in the system by about 5%, right? So if you only remove one significant quantity, that's like 0.5% change of plutonium, right? So if you want to measure that, you want to measure a 0.5% change of plutonium in the system, that's going to be tough in and of itself, right? So, and you need to do that if you want to detect if someone had been doing this potentially. But so you can see here is kind of just like the amount of uranium in the system and the amount of plutonium that builds up in the system over time. The uranium doesn't go down as much because you're slowly feeding in uranium 235 fuel. Okay, but there is certainly a difference between both of these in the, if you're removing plutonium. Okay, so the fraction of uranium, the fraction of fissions coming from uranium is actually going to go up, while the fraction from plutonium is going to go down. And that's actually important because we could look at the fission products potentially to look at to be able to notice any changes here. There are some differences between scale and serpent between plutonium that were fairly large, on the order of 3%, something like that. So if we're expecting to see a 0.5% difference in plutonium, and our models are giving us things that are 3% different from each other, that's kind of tough right there, right? And the other thing is when we look at the uncertainty from the nuclear data, okay, all these cross sections we just kind of take for granted as being, real, handed down from on high. They do have uncertainties, right? And some of them are reasonably high, right? So we use sampler as part of scale, basically just does perturbations to the cross sections according to their covariance. And it basically lets you do a bunch of calculations using these perturbed cross sections, and you can take the variance between those simulations, and that will give you the uncertainty in these results. So one of these things is, the uncertainty in the plutonium concentration at the end of this cycle is like, 1.6%, right? Just due to the cross sections. So if we predicted that our 1% our 1 SQ diversion of plutonium is only giving us a 0.5% change, how are we ever going to notice this when we have an uncertainty from the data that is 1.6%, right? So this is a big challenge. Let's ignore that challenge for a second. Just step back and think about what changes do we expect to see if we remove plutonium from the system. Well, one of them would be, would be that if you remove plutonium, you'll have less plutonium, right? So that's certainly one, but also all the things that are, above plutonium in the actinides, right? So, americium, curium, stuff like that. Those are all going to be reduced, right? So this could be, we're going to have a change in potential neutron signatures from the salt. So any alpha N reactions or spontaneous fission reactions that are releasing neutrons, that's all going to be lowered, right? So if we want to take a sample of salt and measure the number of neutrons coming off of it, right, it's going to go down. We'd also look at the gamma ray signatures from these, but those are probably pretty small compared to fission products in most cases, right? Except if you looked at really long kind of decay times. The fission products, so the other thing, if you remove plutonium, is that you'll have more fissions from uranium, right? So all of the fission products uranium will be there in higher concentrations, right? So you can look at the gamma ray signature difference between these two. And you could also look at, delayed neutrons are just another fission product, right? Or they come from fission products, right? So you could also look at the delayed neutron signature here. I mean, the other thing that would happen is you are going to change the spectrum when you do this. So that would probably cause some other relatively minor changes. We won't talk about this. Main thing I'll talk about is going to be the gamma ray signatures from the fission products, because that one is, pretty easy to measure, right? Take a little sample of this salt. Okay, we have really good, we have really good gamma ray detectors out there to measure things. Okay, and we can, you could pinpoint certain isotopes with certain gamma ray emissions. So take a look at that. So, first of all, just step back, look at the problem. You can say, okay, I have, uranium-235 and plutonium-239. They have different fission yields, right? So I would expect to see in the system that, these plutonium favored ones around, the 100 to 110, right? Those are going to be decreased in this problem if I take away plutonium, whereas the ones down here in this kind of 80 to 90 range are going to be increased when I remove plutonium. Okay. And so, you could go through and you could, look through the list of, all the fission products. And you take a look at, you can cross-reference these with which ones are gamma array emitters, right, when they decay. And you could come up, or, we came up with a list of, hey, here's these things that we predict, might be good, based on the fission yield, the difference between the fission yield of plutonium and uranium, and the half-life. You want that to be kind of that Goldilocks range, right? If the half-life is too long and it doesn't emit anything, if it's too short, then it doesn't last long enough to measure anything, and it's not going to build up very much, right? So, a few examples of things that we predicted here, and actually most of these kind of turned out to be pretty visible in the end. And you could look at the bottle. You could say, okay, let's take a look at a few of those isotopes, and you could see the results pretty quickly that there's some differences. So these two guys at the top, rubidium and krypton, those are both uranium favored nuclides. And as the uranium decreases over time compared to plutonium, their concentration drops. And if you remove plutonium, then their concentration increases. Right, so those are the dashed lines. Whereas the plutonium favored ones, they are increasing over time, and if you remove the plutonium, they go down. Okay, so that's the basic idea. But I mean, again, we're removing a fair amount of plutonium, and the changes aren't super large, so it is a challenge. The other thing is, there's a lot of gamma ray emitters in this stuff, right? There's all the fission products. We looked at, I think we just took the top 10,000 peaks here and used a gamma ray simulation software called GADRIS, looking at, a perfect high purity germanium detector. Okay. And you get this big, huge gamma ray spectra over here. There are two things plotted here. It's just you can't really see the difference, right? Differences are pretty small when you look at it like this. But we made an automatic peak detection and identification algorithm to go through, find where the differences are, and then go back to the reactor simulation, say, hey, what are the isotopes that are emitting that range? And then, how much are those changing? Okay. And so, basically for every kind of time step, and if you could also look at this over time, right? So if you took a sample out and let it decay for a day, to get rid of some of these things, right? Then you might see some other signatures. So these are like on the right, these are the differences between removing something or removing the plutonium and not removing it. And this is for the entire salt. You can get better signatures if you look at the off gas only. Right? So you just have a detection system on your off gas piping, or you could look at your noble metals, and those are actually better. But I'll include this one here. And you can look at a few different metrics for how to evaluate how useful one of these gamma ray photo peaks are going to be, right? So you can look at what the peak area of it is, once you've subtracted kind of the area underneath the peak. And you could look at how much that area changes between these two things. Okay, and the other thing is how far above this Compton continuum, right? There's all this continuum in there, and how far above that is it. Okay, so these are kind of a couple metrics you could look at, and eventually we came up with, hey, here's a bunch of different nuclides that are visible at different times. I mean, there's actually a lot more than this. There's just a few of them. But there's a few different ones that are visible at different times. And you look at kind of like the peak area difference between these two. It's maybe on the order of 1 to 2%. Okay, and that's for 10 significant quantities. So if you're only doing one significant quantity, it's going to be 10 times less than that. So it's not a lot, right? So if you aren't removing as much, the uncertainty is the uncertainty. I mean, both in your detection system, but also just from your nuclear data is going to dominate over anything to change you might see here, even if you have a perfect detection system. So kind of like summarizing all this this material accountancy stuff, right? Is that it's going to be challenging to do material accounting for a molten salt reactor. You can't rely on just counting things. And the expected changes in concentration if someone were to do a protracted removal are pretty small, okay? So, I mean, one thing is maybe we just don't look at, maybe we could try to exclude the possibility that someone would be able to do this over a long period of time through other kind of physical protection measures and whatnot, right? So that's certainly an option. We looked at gamma ray and neutron signatures. I didn't talk about the neutron stuff here. It's going to get a little much, right? But so we found some promising gamma ray peaks that we could, showed some, significant, maybe in the statistical sense in this case, right? But changes that are visible. The off gas and the noble metal streams, I didn't show them here, but they're less crowded, kind of, and they do give some better signals. You also get some pretty good neutron signatures from the salt. So, those spontaneous fission alpha and delayed neutrons, those were all actually pretty good signatures, although, it's a little bit harder with neutrons, you don't get any spectral information from them. So you need to do multiplicity counting, but then there's a lot of curium. So that becomes a challenge. Or you could do, total neutron counting, which might be more effective. But anyway, the other challenge is that the uncertainties are super large, the uncertainties from nuclear data, right? So this will have to be reduced somehow if we want to be able to detect these things. One option is looking at, instead of just looking at kind of like a single point, you look at a time series, right? You can look at how these things change over time, and then can we make a better, can we get something that has less uncertainty that way? Could we look at multiple signatures together, right? So, instead of just looking at a single photo peak or something like that, you could look at a whole bunch of them. You could look at photon signatures, neutron signatures. You could do mass spectrometry of the off gas. You could do a bunch of other things to try to, and by synthesizing all those things together, you can reduce the uncertainty that way. Another one, we get better nuclear data, right? Just new evaluations are coming out. They come out. I mean, I don't want to say regularly, but somewhat regularly, right? So lower uncertainties on that would obviously improve this. Or you could use nuclear data that is tuned to your particular system, right? So after the reactor has been operating, right, you would have better information about what your cross sections actually are for this particular system, and you can tune the cross sections such that you're now less uncertainty. Okay, now kind of shifting gears from the salt stuff onto radiation transport, right? So, in general, right, radiation transport, we have a source of radiation, you have some material distribution, and you want to try to find the flux or reaction rate, right? Or in an eigenvalue problem, you don't know what your source is, right? You want to calculate your eigenvalue and your flux, right? There's two ways you could go about solving this. You could do this deterministically, so you're trying to solve the transport equation, right? You have to discretize your phase space and you solve for your flux over the entire domain, right? So the downside of this is you have this discretization error from having to discretize the transport equation. With stochastic methods or Monte Carlo methods, right? You're simulating the random action of a bunch of particles. The good thing is you have continuous treatment of space, energy, and direction, right? And you tally the results over different parts of your system. Downside there being you have statistical uncertainty, right? So these are major challenges. I just want to put the equation up there to scare you a little bit. I'm not going to talk about it. You guys should know that by now. But solving this system, right? It has 6 dimensions. It has 7 dimensions if you want to look at time, right? It's hard to solve, right? And when you do this discretization, you're breaking this up into spatial meshes, solving at a bunch of angles, you have a multi-group approximation, right? All these things bring error into your result, okay? That can be hard to quantify too. And, for example, right, at every single mesh point in your problem, potentially you have hundreds of different angles, right? And if you want to have more angles in order to get a more accurate result, that ends up costing more computational time, right? Quickly become pretty challenging and memory intensive, right? So in Monte Carlo, you're randomly sampling from, the history of these different particles, using these known probability distributions. It's great because you have continuous geometry and continuous energy and everything, right? And you're tallying each of these individual results as they interact with stuff in your system. The big problem, as I mentioned, is uncertainty, right? You need a lot of samples to get a low statistical uncertainty, right? So if you want to get 1% uncertainty in something, and you're dealing with a totally analog case here, if this are just the detector counts, right, you need to get like 10,000 counts in your detector to get 1% uncertainty, right? So if you're dealing with like a shielding problem, then, the number of counts at your sample, right, is going to be super low by design, right? You want to design a good shield, not many things can get through, right? Or if you want to get detailed distributions of something, right? So if you have a reactor and you want to get results down at the pin level and you want to get it resolved axially well, right? It's really challenging, right? You need a ton of samples to get that, right? It can be prohibitive. So, in terms of reactor analysis, right, if you're doing deterministic, there's kind of the low order diffusion kind of methods where you get rid of all your angular dependence, and you can do nodal, so you get rid of a lot of, you have large spatial meshes. Works really well for large reactor problems, especially if you have some stuff you have a lot of experience, right? So light water reactors, if you have 50 years of experience, you can tune all these things, it works pretty well, right? Newer reactor designs are a lot, more challenging because they don't have all this data over the years. They're also a lot smaller, so there's higher leakage, right? And a lot of, the error from diffusion comes from modeling the reflector and leakage, right? So that's challenging. You can use high order transport methods, but these also require a lot of computing resource, potentially thousands of processors, which is expensive. Monte Carlo methods, again, so they have all this higher computer power in recent years has made this more feasible, right? But the local tallies are still going to have high uncertainties if you want to get a lot of detail in your problem. So it's not necessarily feasible for routine analysis of reactors, okay? Especially if you want to do transients or coupled problems and stuff like that. So one thing you could do is you could look at hybrid methods, right? So trying to take advantage of the good things about Monte Carlo, the accuracy, but still trying to take the speed and detailed information you would get with deterministic calculation, right? So, some examples of hybrid methods would be, you use a deterministic solver to solve for the adjoint flux, and you use that to accelerate your Monte Carlo solution. You could use Monte Carlo to calculate accurate diffusion coefficients in your system. Or the one that I'm going to talk about is using the fission matrix eigenvalue formulation, which is a little bit different. So the fission matrix is kind of like an old concept that has seen more interest in recent years. So it's kind of been around for a long time. First discussed in the 50s even. but it was kind of more just like as a theoretical concept. It wasn't really, didn't really have much practical use. Recently, people have been using it to accelerate source convergence, use it for diagnostics. If you want to calculate higher eigenmodes, just fundamental eigenmode, you can do that, and some time-dependent methods as well. So some of the new methods that I have developed based on the fission matrix includes this rapid code. So this was originally designed for spent fuel problems, for spent fuel pools and spent fuel casks. We realized that we could actually use it for reactor problems and do a lot of interesting stuff. And it's designed to be really fast. So like, sub-second up to maybe a minute for some really large problems. So in theory, this is super simple, okay? It's basically just saying that the fission source in some spatial cell is a result of, you can be considered as, fission neutrons in other cells are going to cause fission in this cell, okay? And they're related by some coefficient, and that's the fission matrix coefficient. So these coefficients are the number of neutrons created in one cell due to a neutron born in a different cell, okay? And you could write this, in a matrix format, right? And then it's just a linear system to solve for K and for your source distribution. So I mean that all sounds fine, right? But the challenge is how do you calculate the fission matrix, right? So you solve one problem by creating another. That's usually what you do in most of these problems, right? So I mean one thing you could do is you could just do a bunch of fixed source calculations, right? You could put a little source in a little area of your problem. You can tally, the induced fission source everywhere. That would give you one column of this matrix. But this gets impractical as the system gets really large, and it requires small cells if you want to do this accurately. The other thing you could do is you could do like an on-the-fly kind of thing. So you could do a regular K calculation of Monte Carlo, and then you just every neutron you tag it with the source. With what cell it was born in, and then what cell it causes fission in, right? And then you can just tally that result. Okay, this lets your cell be larger because you have some intra-cell information, but it also means that you need large cells in order to avoid memory limitations, right? So matrices get large quickly, right? So you need to be careful there. So I've actually used both of these methods for different purposes. The first one, the fixed source calculation one, sounds really bad, but if you use some geometric similarity assumptions, you can reduce the number of calculations you need to do by a lot. And one other interesting thing, I mean, is kind of the crux of doing any of these fission matrix type calculations, is that you can potentially combine different fission matrices together. If you calculate them under two different conditions, you can actually just combine them and get some combined condition without recalculating it. Okay, so for example, if you calculated a fission matrix where you have two of one assembly type and two assemblies of a different assembly type, right? And you calculate the fission matrix, and you want to know what the fission matrix is for some combined system, you could actually just take the rows from each of those matrices and put them together based on the destination. So that'd be the row rather than the column. And then this combination could be based on assembly type. It could be done on fuel or moderator temperature or control rod position, right? So you can interpolate between all these different conditions. And it works really well when the material change isn't too large. So like temperature gradient, stuff like that, it works really well. If you have two super dissimilar materials, it might not work as well. But there are some corrections that you can do for that. So, one thing we first did on this was looking at this for the Penn State Brazil reactor. It's a trigger reactor. And calculated the fission matrix basically at a bunch of uniform temperatures. Okay, this is actually a really bad way to do it, okay, but it shows kind of how well this works, okay, and then at some different control rod elevations, okay, and then we basically say, okay, well, now we can just combine and interpolate these fission matrices for any temperature distribution within, 300 to 600, but it doesn't have to be uniform. It can be anything. And control rod height. Okay, so we get anything you come up with, we could interpolate this fission matrix. I mean, it would be an estimate of it, right? But the estimate turned out pretty good. Now we can also couple this to thermal hydraulics, right? So we did use trace to get the fuel and coolant temperature distribution. And then, so the fission matrix would provide the source distribution, which is proportional to the power, and the critical rod height with this temperature distribution. Then we can go back and forth with trace, and we can determine, what is the critical rod position, the critical temperature distribution, or, we could look at if we want to try to hit a certain power, where do we need to put the rods, et cetera, and we do this iteration back and forth. And I mean, basically it worked really well. So, looking at these different power levels, okay, we can predict the control rod position, and then you end up with some very small errors, on the order of 1%, something like that. And it's very small. We later did some more accurate ones with some improved, not assuming uniform temperatures, and that worked really well. We could also use this on different core loadings, right? So this is core loading 4 was in the 60s, and then core load 58 was a few years ago. Okay, so this has a lot of burn fuel. This core loading 4 had a lot of fresh fuel. So these are if you look at each of these core loadings and you go up in power with this coupled calculation, the difference between just running a Monte Carlo calculation and running fission matrix is, very low, under 40 PCM for all these cases. And, RMS, 3D RMS error even is, less than 0.5%. Pretty good. And you can do all the solutions super fast, right? This is less than a second. And this is also super not optimized. And, it's on a single processor and everything. It's also been validated against historical data for the reactor. So back when I was a fresh core, there's a bunch of tests done. So we compared that to look at what is the instrumented fuel element temperature, okay, and compare that to our calculations fission matrix at different power levels, right? Corresponding and different control rod positions along with that. And then also, how much the reactivity changed in each of these situations, right? So it matched up really well. We can also use this to calculate things like detector response. So this is a new thing one of my students are working on. So, one of the things is that the power calibration of the reactors is not perfect, okay? We kind of assume that it's linear with the detector response, but the detector response per unit power is actually different depending on the conditions. So, what we did here is we looked at, okay, we calculated a detector response function, which is what is the response of my detector due to a source particle in a given rod. And you can do this with MCMP pretty easily, and you can actually use some adjoint acceleration to make this a lot faster. And that works pretty well. So you calculate, hey, if I have a source in one of these rods, how much do I get in this detector? Then we could calculate the source distribution using our fission matrix thing, right? And that could be dependent on whatever conditions you have, whatever rod positions, temperatures, right? If you put the rods in, that tends to push the source out towards the edges. So you're going to get more response in these detectors per unit power. And then, you can kind of combine these together to get, well, what is my detector response under these situations? And you can see, this just shows where our detector response is coming from, which of these cells is it coming from. So this can help us predict the true reactor power under different conditions in order to, better estimate burn up of different rods and experimental setups and stuff like that. We've also used it on using it to calculate the reactivity for point kinetics equations, so you could use the power or sorry, you could use whatever your temperature distribution is to estimate what the reactivity is, and then you can solve the point kinetics equation, and then you can update your point kinetics using an updated fission matrix calculation. And you can update the temperature. We looked at this for some prompt pulses for the Penn State reactor, and you can see, they look pretty good here. This is something that needs some more work though, but as proof of concept, this worked pretty well. And these are just some pulses at different reactivity insertions. Another one is on nuclear thermal propulsion, another application of this. So NASA is looking at nuclear thermal propulsion to get to Mars. It's a pretty good way to get there. High specific impulse and high thrust. Right now they're using Monte Carlo to do these, but for things like transients and stuff like that, it's probably not going to work very well. So I want to use a fission matrix in this, see how it worked. So this is, one of the core models for one of these proposed designs. So it's using a uranium zirconium composite fuel and zirconium hydride moderator blocks. And this system is pretty small, right? So it's like 66 centimeters wide, meter tall, something like that. It's got control drums on the outside. So, if you want to do this accurately, you need to, these temperatures get up to like 2,500 Kelvin or something like that. So, there's a lot of temperature feedback here, right? And so if you want to do this accurately, you need to do the back and forth between the neutronics and the thermal hydraulics. So, you're using your temperature distribution to calculate power distribution, using power distribution to calculate temperature distribution, going back, right? So, if you want to do system analysis, you want to do transients, you need to do a lot of neutronics calculations, and that's tough if you're doing it in Monte Carlo, right? So, we looked at this with the fission matrix technique here, right? So basically just calculated this, did 20 the kind of database calculations, right? At a few uniform temperatures and a few control drum angles with, a relatively small number of cells, around 2,000 cells. And, so this just generates a database. I would say this is like cross-section generation, if you want to think about it that way for deterministic codes. You're doing a set of calculations to determine this database, and then you're combining it. So, we did this with a few different profiles, so we assumed it was all uniform. We did these database calculations, but then now let's do like this case that goes from, 300 to 2000 Kelvin, within the space of a meter, and then radially it's changing as well. And then, basically it worked really well. So, it lines up almost perfectly. If you look at the axial source profile, if you look at the 3D source down here, there's a little bit of error, but that's really mostly because of the Monte Carlo uncertainty is pretty high. So it's hard to, if you want to get a 3D result, it's really hard to get a 3D Monte Carlo reference because we have a lot of uncertainties. So yeah, worked really well. You can look at how does this work at different maximum temperatures. It works well. You can look at what does this axial source look like. You can look at radially what the source looks like. Again, these things are on the order of less than 1%. And you can look at the normal, like the 3D source error is on the order of like 0.5%, pretty good. And it takes a couple seconds versus the reference calculation was on the order of 150 hours to get that. So we're interpolating on control drum angle, right? So we have these control drums that come in to shut it down. And, again, we did a few calculations to get the fission matrix under those conditions, and we're interpolating back, and that works really well. So again, control drums work well. So, it has a lot of potential for these NTP applications. definitely not gonna have enough time to get all of this, but I did want to talk quickly about this other one. So what if we have like a large system, like a PWR, right? So something like the Beavers benchmarks, like 197 assemblies, 17 by 17, 100 axial levels, a few different assembly types. This means there's over 5 million tallies. Okay, pretty tough. Pretty tough if you want to get a detailed 3D distribution here. So I was talking about the other way to do a fission matrix calculation, using fixed sources. Seems like this would be a really bad place to do it, but it's actually not bad. So if you put a source in a single region, okay, and you tally the fission distribution everywhere within a single axial level of this single rod, you get a single column basically of your fission matrix. Okay. In theory, you would repeat this for every single pin and every single axial cell, which wouldn't be very practical, right? If you have millions of them. But this fission matrix is very sparse. So neutrons don't travel all the way across the core, so a lot of the elements are basically zero. You don't travel very far radially or axially, so you can basically say, hey, I'm going to limit this amount. And I can use, geometric similarity, right? So a neutron going from here to the next assembly over is probably about the same as from this one going to the next one over, as long as they're the same assemblies, right? And you can do the same thing axially. So if you have a core of identical assemblies, right, you can kind of do this just for a single octant of one assembly. So 39 fixed source calculations, you could get an approximate estimate for what your fission matrix is for this entire reactor, which is pretty cool. So, single calculation will get you one column. You can do a single octant, which gets you a little more. It uses geometric similarity to basically estimate the whole thing. So that does break down at the reflector. So if you want to get an even better answer, you could use a correction factor for the reflector. Not going to get into that too much, but end result is you get an extremely accurate result. I mean, I think the R2D RMS is like less than 0.5% here, something like that. And it takes like 30 seconds to run this on 20 cores versus 80 hours for a Monte Carlo result to this level of accuracy, or to this level of precision, I should say. And then the other thing is you get really low uncertainties in your local results compared to Serpent. So for these calculations, these are the axial source distributions for two individual pins. Okay, and so they're both on here. It's just the Monte Carlo result has a lot of uncertainty going up and down, whereas this rapid result is looking pretty good in the middle there. So to kind of summarize, this fission matrix method is a powerful way to solve the transport equation. Pretty new method of doing this, and pretty interesting in my opinion. You can basically reproduce your Monte Carlo result exactly if your reference conditions are met in your database. And if you're not at the reference conditions, then you can interpolate on temperature, control rod position, whatever, and you can do that quite effectively without too much extra challenge or error. And it works really well on coupled problems. It's also super fast to do transients and stuff like that. You can repeat these calculations over and over again. A lot of interesting ways or places to do future research here. So I want to work on this on unstructured mesh. Right now, I've only done Cartesian meshes, but it also should work with an unstructured mesh to do that on some weird geometries. Integration into MOOS. So MOOS is the Multiphysics Object-Oriented Simulation Environment, maybe. It's INL Multiphysics Framework. And if we did that, then it would really enable easily coupling into other codes to do more multiphysics stuff. I want to look into more transient capabilities. It's kind of just touched on the surface of that with some prompt transients, but I think there's a lot of other interesting stuff that can be done there. Depletion, doing depletion with it is interesting. Some folks at Virginia Tech have also done that. And I think that can work well. And also just testing it on more reactor types, getting it out there, get a more polished product. So I do want to acknowledge all my students that have worked hard on these projects, so on the safeguards, the fission matrix ones, detector modeling, stuff like that. And there are a few grants that have supported this work. And with that, let's stop and see if anyone has any questions.
All right, thank you very much. I'm going to go into the chat first. And then, as always, if people have questions, please raise your hand and I'll call on you and you'll be able to ask the question. Or if you want to post it to the chat, I can read it for you. Or if you're here, of course, you can raise your hand and ask it yourself. So the first question comes from Robert Hayes. And he asks, have you published any of the MSR results yet?
Cracking the whip, my grad students right now. So, but some of that's been published in the summer INMM conference. And then publication is hopefully happening soon, within the next few months, hopefully, for the rest of the results.
Okay, thank you. Any questions from the face-to-face? Nope. None? Okay. Any other questions from our online participants? Oh, we got one here. So William Down asks on the chat, the fission matrix results look very promising. Could you comment on the amount of memory/storage that is required to store the fission matrices compared to more traditional cross-section methods?
Yeah, absolutely. So, it's a great question. One of the benefits of it is you're taking more information from your high fidelity transport problem than just your cross sections, right? So it certainly does require more memory. And I mean, the answer is with everything, it depends, right? So we haven't run into any limitations yet. If you want to, the larger the size of your matrix, obviously the storage increases and the number of cases you need increases. We've actually come up with some interesting ways. We don't need to store the entire matrix for all the perturbations. So it actually works out pretty well that you can just store one matrix that has all the elements, and then you can store basically a diagonal matrix, which is just a vector that has basically that stores the perturbation information for each of those, and that actually works quite well. I haven't found any cases that doesn't work well on it. It drastically reduces the storage requirements, which is pretty good.
So Steve, I have a question.
Okay.
So William, one area of interest is taking into account the core environment. And you show some boundary factors for the reflector. But what about unlike assemblies or other challenges, rodded versus unrodded? How you take into account, because I think you're generating this fission coefficient, mathematics coefficient for single assembly, right?
For that case, so I guess there's two different ones. One of them is with the rapid one you're calculating it for single assembly basically, and then assuming you can translate that around. When you have things like control rods that cause the strong gradients and stuff like that, it causes some errors. So you do have to do some basically supercell kind of calculations with the fission matrix, and it basically just comes up with like a correction for each set of dissimilar assemblies. You can it will come up with a correction for that, and that works with the control rods and stuff. So I mean, that one definitely has some it's a challenge. So I mean, that's kind of the reason why I have been focusing more on the other methods where you calculate basically the full matrix and you don't have to make any assumptions about that.
Yeah, I completely agree because this even will be better approach, especially for the current smaller reactors like
Yeah.
microreactors, right?
Yeah, that's my plan for it. So hopefully testing it out with some of these micro reactor concepts.
Yes.
It'll work pretty well.
Yeah, thank you.
Excellent question.
Okay, any other questions for our speaker? Around here, don't see any. We're right at 5 o'clock, so the timing is perfect. So I'm gonna go ahead and if there's any other questions, I'm gonna go ahead and close the seminar. Thank you very much for our speaker. To our speaker, I appreciate the presentation. It was really awesome. And I look forward to seeing you all next week at next week's seminar. So thank you very much.
Okay, thank you so much. Appreciate the invitation. It was a lot of fun. Thanks.
Thank you, William.
Hopefully I'll visit in person soon.
Yes, yes, definitely.
That would be nice.
Thank you.
All right.